So welcome back again. So we are going to continue in our meeting with David's presentation, which is hunting for heavy C prime with IceCube neutrinos and gravitational waves. So let's see what David has to say to us.
Okay, good afternoon, everyone. Today I'm gonna show this paper that is a proposal for Basavento, which was a former postdoc from Nicolas Bernal. That is about a model that contains a heavy prime that can be tested through IceCube neutrinos and gravitational waves. So in this model, they propose a gauge B minus L extension of the standard model, which is to gauge the symmetry, accidental symmetry of the standard model, which is a baryon minus lepton number, into a gauge symmetry. That generates a new gauge boson, which is the C prime. With this extension of the standard model, they can solve the three phenomenological problems of the standard model. They can render or they can explain the neutrino masses and neutrino oscillations, via Taiwan CISO. They can generate a viable dark matter candidate using freezing production of a chiral fermion, which of a new fermion, which it would correspond to the right-handed neutrino, and they display also the baryon of symmetry of the universe using the leptogenesis mechanism. So, and they wanna relate the phenomenological consequences of this model with IceCube neutrinos. That IceCube recently observed events for neutrinos of PV with PV energies of PV. So that would be the order of the right-handed neutrino they are gonna introduce, and there will be also the order of the processes that give the proper let's play neutrino masses and baryon asymmetry of the universe. So, and they also relate this with gravitational wave production in the early universe via cosmic strings that are generated from the spontaneous symmetry raking of the B minus L symmetry. So, is the standard model with an extra gauge symmetry that is B minus L. So the quarks and the leptons have the usual lepton and baryon number assumptions of them, and this hills remains uncharged under this B minus L symmetry. But in order to cancel out gauge anomalies, they have to introduce at least three heavy right-handed neutrinos. With the introduction of this, you need to introduce three new chiral fermions in order to have a quantum field theory that the one loop calculations would be consistent, will converge. So it is a theoretical requirement to introduce new chiral fermions. The advantage of doing this is that you can use them as right-handed neutrinos and introduce via this Yukawa term that is shown in the equation 1 um, an interaction with left-handed neutrinos and therefore generate spline neutrino masses via type 1 CSO. So the second term in the equation 1 would be the mass of the heavy neutrinos, which will be proportional to the scale of spontaneous symmetry breaking of B minus L symmetry. So they have to use, they have to add one singlet or only one new scalar that is the responsible for the spontaneous symmetry breaking of the B minus L symmetry. And with this, they can render this Majorana this Majorana mass term for the right-handed neutrinos, which leads to this mass matrix for line neutrinos, which you can you can tune in order to satisfy all the constraints that come from neutrino masses and mixings. Of course, they add 3 right-handed neutrinos, but one of them they will they are going to use it as a Darmaret candidate, and they will be produced via freezing mechanism. So the coupling, the Yukawa coupling of this right-handed neutrino will be small enough in order to coupling to the C prime boson must be small enough in order to generate freezing to explain the Rayleigh density of dark matter via freezing mechanism. So now let's talk about the freezing. The freezing is a mechanism where the initial assumption is that dark matter is not in equilibrium with thermal bath, with the standard model thermal bath. So there are and another assumption is that the number density of the yield of the dark matter is initially very small in the early universe, and dark matter is populated via three type of processes that can be the case of the C prime boson into dark matter candidate, the case of the dark Higgs. This new scalar will be a Higgs-like particle that I'm going to call just dark Higgs, and they can decay in order to produce the dark matter candidate. Or there is another processes that lead to Rayleigh density, that is scattering between standard model particles into right-handed neutrinos. That's for example, in the equation A, we have the condition that must satisfy the dark matter in order to avoid thermal equilibrium with a standard model bath. That is written in terms of the production of dark matter particles via decays and scatterings of the case of heavy particles and scattering of standard model particles with dark matter candidate. So basically, the initial abundance of dark matter is negligible. The heavy particles decay into dark matter, or the standard model particles annihilate into dark matter, and the yield of dark matter starts to increase. And finally, there would reach uh, uh, a point where is number density would get fixed and at some temperature. That temperature is known as the freezing temperature. So this yield or the abundance of dark matter freezes and remains constant. And this abundance has to be compatible with the abundance observed by Planck collaboration, the dark matter abundance that 12. Okay. Now, regarding the leptogenesis, they want to explain baryon asymmetry of the universe, that is another problem of the standard model. Basically, the standard model cannot explain what is more matter, cannot explain quantitatively why there is more matter than antimatter. Because if you think, nothing really forbids that there will be equal amount of a matter and antimatter, and they will annihilate the and produce radiation. So we need also a mechanism that explain what is more matter than antimatter. And that's problem why is there more matter than antimatter is known as the baryon asymmetry of the universe problem. One way to explain the baryon asymmetry of the universe is via leptogenesis mechanism. What is leptogenesis? It's a mechanism that explains the difference between matter and antimatter via the decay of a heavy Majorana CP violating decay of a heavy Majorana terminal. The contribution to the violation of the electron number will come from the interference between contributions of 3 level and 1 loop level of the CPE violating terms of the decay of the of these heavy right-handed neutrinos. So they found, for example, in this equation team 9, this violation of lepton number, which would be transformed into violation of lepton of baryon number, because baryon, the number baryon number is the property that tells you the difference between matter and antimatter, not lepton number really. If there is a violation of baryon number, there will be more matter than antimatter. So this they need to transform this lepton number violation into a baryon number violation that proceeds via Sphaleron in the early universe. What is a Sphaleron? A Sphaleron is uh, a pseudo particle that is produced in that is a consequence of the spontaneous symmetry breaking in the early universe that correspond to transitions of different degenerated vacuum. I mean, for example, the standard model, the vacuum of the standard model, the vacuum state of the standard model is not unique. You have several vacuum states with the same that are degenerated but they are not equivalent because they have different topological charges, different topological properties. So there could be a transition between these different vacuum in the universe, in the early universe, mediated by this Sphaleron topological object. So, and it's known that Sphaler concern the same property as the standard model, that is B minus L. So a difference in lepton number would be compensated in a difference of baryon number. So they would transform this lepton number asymmetry into baryon number asymmetry. So the lepton number asymmetry can be written, as they say, show here, into the difference between the case of right-handed neutrinos into particles and antiparticles, CP violating the case. The CP symmetry is that the symmetry that distinguish between particles and antiparticles, right? So, and can be also constrained in terms of neutrino masses observables. So, that would lead to this contribution to the generation of asymmetry of lepton number, as shown in the equation 12. And they can also adjust that the parameters of the model in order to obtain the number of asymmetry baryon to photon ratio that is required by cosmology, that is this one. That would, of number of baryons and antibaryons, the number of matter and antimatter, that is required in order to explain why there is more matter than antimatter. But okay, so they have the model with these. They have solved the three problems of the standard model: baryon, asymmetry of the universe, matter, dark matter, and neutrino masses. But they have another consequences in the early universe. For example, the spontaneous symmetry breaking of this B minus L symmetry would lead to a new topological defect that is a cosmic, well, it's not new, it's also present in the standard model, but in this case, we have also contributions for the cosmic strings. The cosmic strings that are generated in these phase transitions will also radiate energy via gravitational waves. And they want to study the gravitational waves spectrum coming from these topological defects coming generated in the because of the spontaneous symmetry breaking of the B minus L symmetry. And so they study the energy of the energy the energy that is irradiated by the an oscillating loop of a cosmic string would be proportional to the quadrupole moment that would depend of the characteristics of the string formation, of the process of the string formation. So here they consider they want to find the amplitude of the gravitational waves as a function of this frequency. So they consider this expansion in terms of the normal modes of the oscillation of these loops, as shown in the equation 12. So they want to find the evolution of this density of energy of gravitational waves in terms of the frequency that would redshift because of the expansion of the universe. So gravitational waves are radiation, so the energy density with scales as a to the minus 4. So the equation for the evolution of the density of the gravitational waves in terms of the frequency and the energy would be as shown in 12. But as I was showing, this can be studied in terms of the small topological small objects that form because of the a smaller scale from these gravitational waves. That can be studied. The number density of these loops of gravitational waves would depend from the factor beta, which is which can be written with depend of the equation of the area of the universe which you're talking about. So for they have to integrate us here our time, and they found this expression for the density of gravitational waves, which in the case of uh, a gravitational waves formed during a radiation dominated era would give this spectrum that would yield this spectrum. This spectrum can be related to okay. Sorry. No. This is so. This spectrum will also depend on the properties of the model, like the C prime boson mass and the gauge coupling, and you can constrain these two parameters in this plane via these gravitational wave experiments like LIGO, LISA, and so on. So we have as a conclusion, we have a model. They present a model that solves the three problems of the standard model, and that has important cosmological consequences that lead to a form that you can study via analysis of the gravitational wave spectrum for the phase transition, for the spontaneous symmetry breaking of B minus L symmetry in the early universe. So that's it. Thank you.
Okay, let's thank David for his presentation. It's time for questions. Anyone has? Why in the standard model we have the CP evaluation, the CP evaluation in the quartz? Why the CP evaluation in the quartz cannot explain the variance symmetry in the universe?
Because the Higgs is too free. The variant asymmetry will also depend on the Higgs mass. The Higgs mass of the current Higgs mass is just too high to explain correctly the variant asymmetry of the universe. This would be like many orders of magnitude smaller than this number that is required for cosmology.
Does anyone has any question? No? If not, so let's paint a bit again. So that's all for today. Thank you very much for looking us on YouTube. Thank you very much for the people that attended the meeting. Like and subscribe, and see you next week.